So you're walking around, kind of minding your own business, when all of a sudden this farmer person comes up to you and he's like, "Hey, I've heard that you're really, really good at math, so I would like you to help me with this problem. I'm trying to build a pasture to put all my cows in. However, I only have a limited amount of fencing available, and of course, I would like to make the largest field so that I can put as many cows in as possible and not have to spend a lot of money." When you think about it, and you're like, "Okay, well, circles give the most amount of area for any perimeter you have, so maybe you could build it like a circle." And he says, "Yeah, I guess so, but I only have straight fences and I only have square corners, so I can't really, make a curved fence. I can't make it into a circle." And you think about it a bit more and you're like, "Okay, well, squares are pretty close to circles and they've got the straight sides and they've got the right angles, so maybe you could make it like a square." And he says, "Wait, there's one more part to this problem. There's this wall that I would like to build next to, because I don't have to build fences on the side of the wall, and that would save some money." And you think about it, and you're like, "Oh my God, well, I guess you have to make like the wall side pretty long so that you can take advantage of not having to pay for the wall side. But then that messes up your area, because if you make it too long, then the area becomes really, really small. And I really don't know. I can't help you. Oh my God, I've totally failed you. I have no idea how to solve this problem." So it may not be immediately obvious how this is related to the product rule, but that is our video today, and we'll explain how everything's related pretty soon. And of course, we're also going to talk a little bit about that other rule, which is derived from the product rule, and then that's the quotient rule. So the product rule tells us how to differentiate a function that is made of two things multiplied together. So let's take a look at this pasture example. Now let's set up our variables. We'll say that L is the dimension parallel to the wall, and W will be the other dimension. And of course, we care about the area, and we know that the area is simply L times W, the length times the width. And oh look, this is two things multiplied together. However, we should really, before thinking about derivatives, we need to make this into a proper one variable function. And of course, we know there's a limited amount of fence available. There's only 1,000 meters of it, and that has to equal kind of everything that we're building. So we're building one length and two widths. So we have the relationship 1,000 equals L plus 2W. And of course, we can rearrange this to find that W equals 500 minus L over 2, and we'll rewrite that original area as a function of L only. So we have A at L is equal to L times 500 minus L over 2. And of course, this is still two elements multiplied together. But why do we care about finding the derivative of this thing? Why would that help us solve the problem? So let's think about it for a moment. When we build a really, really long pasture, the width has to be really small because we have a limited amount of fence, and that makes the area quite low. When the L is too low, well, the area is also low because now you have this really, really thin pasture that isn't really area efficient. So if we kind of make like a rough graph of A at L, so we can see that, at the low L it's quite low, at the high L it's quite low, but somewhere in there is going to be that perfect point where we're going to get the maximum area. And of course, if you think about it a bit, everything before it has to have a slope that is going up, and everything that's after it has to have a slope going down. And now at the point itself, the slope is going to be 0 because, it is the peak kind of the graph. And of course, this is what relates this problem to derivatives, because the derivative of the function A at L at that point has to be 0. We can find the optimal dimensions by simply finding the derivative and solving where it equals 0. So how can we use the product rule to help us? Of course, you can kind of multiply everything out and do it that way, but we're going to talk about it in terms of the product rule because it can be applied to way more complicated things. So let's look at a graphical representation of what the product rule is. So let's say you have a length and a width. Well, your area is obviously going to be your length times the width. Now let's say you want to change up L and W a bit. Let's say you change L by delta L and you change W by delta W. Well, what is the new area? The new area is going to be L plus delta L times W plus delta W. But how has the area changed in relationship to our changes in the L and the W? Well, the delta of A, the change in A, is equal to the new area minus the original area. So we're going to do that. We're going to do a little bit of rearranging here. The length times width cancels out with the length times width, and we get that. So we got kind of a weird equation. We have a bunch of deltas in there, but how does this relate to the derivative? Well, recall that the derivative of A with respect to something is just the limit as delta x goes to 0 of delta A over delta x. So instead of using x, let's use L, because obviously we care about the derivative with respect to L. It is the independent variable. So let's divide both sides of this by delta L and take the limit as delta L goes to 0. Okay, so we're simply going to divide each term on either side by delta L, and then we'll take the limit of all of those as delta L goes to 0. Okay, now we're going to apply the definition of the derivative above. So every time we see delta something over delta L, as delta L goes to 0, we're going to replace that with the derivative of that thing. So we're going to do that, and we're going to get the derivative of A is equal to W times the derivative of L plus L times the derivative of W, and the last term is going to go to 0. And of course, all the derivatives are with respect to L. Okay, we can write this in a more general form. The derivative of two things multiplied together, f and g, is equal to the first thing times the derivative of the second, plus the second thing multiplied by the derivative of the first, and that is the product rule. So let's see how it works. Let's apply this to the function that we had before. A at L is equal to L times 500 minus L divided by 2 in brackets. So we're going to start off. The independent variable here is L. The functions that are being multiplied together are L and 500 minus L over 2. And we're going to figure out the derivatives of those. The derivative of L with respect to L is simply 1. The derivative of 500 minus L divided by 2 is negative 1 over 2, just by the power rule here. Okay, we're going to apply the product rule. We'll say the derivative of A is equal to W times the derivative of L plus L times the derivative of W. And we're going to sub in all those things that we have there. Okay, and that's going to give us 500 minus L over 2 times 1 plus L times negative 1/2. And that's going to give us, after some simplifying, 500 minus L. Okay, so now we can solve for that optimal point. We simply have to plug in that the derivative is equal to 0. 0 equals 500 minus L, and L is 500. You can also get W because we know that W is equal to 500 minus L over 2. So now we get that the largest pasture would have the length 500 and a width of 250, both in meters. Now, let's talk a bit about the quotient rule. We can find the quotient rule simply by messing about with the product rule. And it relies on the fact that you can rewrite a quotient f divided by g as the product f times 1 over g. Okay, so let's apply the product rule to f times 1 over g. And that's going to give us f times the derivative of 1 over g plus 1 over g times the derivative of f. Now, we can't really differentiate 1 over g with respect to x here because, x isn't in 1 over g. However, we can apply the chain rule by using the variable g as an intermediate variable. So we get the derivative of 1 over g with respect to x is equal to the derivative of 1 over g with respect to g, which is doable, times the derivative of g with respect to x. Okay, so we can simply solve for the derivative of 1 over g with respect to g. That's going to give us negative 1 over g squared, and multiply by the derivative of g with respect to x. Okay, we're going to sub all that back in. We're going to do a little bit of rearranging. We're going to factor out 1 over g squared, and that is going to give us, finally, the quotient rule, which can be expressed as the derivative of f over g with respect to x is equal to g times the derivative of f minus f times the derivative of g all over g squared. And that is the quotient rule. Cheers.